In our last lesson, we learned how to calculate the probability for something like flipping a coin and what the probability of getting 3 heads would be if you flipped it 5 times. Now what we want to do is look at a probability distribution for flipping a coin 5 times. Um, if we flip it 5 times, it's possible we won't get any heads. We could get 1 head, 2 head, 3 heads, 4 heads, or 5 heads. And we want to look at the relative probability of each to get a sense of what happens when we flip a coin 5 times. So let's explore that a little bit further. Okay, so here was the formula we had from that last lesson. Just quick reminder of a few things. P is the probability that you will succeed. So 1 minus P is the probability that you will fail or not succeed. R will be the number of times you succeed, and N minus R would be the number of times you fail, because it's when you did not succeed. And this is the number of ways you could organize R successes and N minus R failures. So if you were to line them up as S's and F's, you could count up the ways that you could arrange your successes and failures using that combination. So that's why the formula works. Now what we want to consider is the probability distribution for flipping a coin 5 times. All right, so what are the possible outcomes? Okay, so the outcomes would be, we could count up the heads and the tails, but it's just as easy to just count up the number of heads that we would get. So as I just stated, it's possible that you get 0 heads. It's also possible that you get 1 head, 2 heads, 3 heads, 4 heads, or 5 heads. We can't do any better than that if we flip this 5 times, right? So using our formula, we could figure out our probabilities for each outcome. Okay, so the probability of this, according to the formula, would be 5 objects taken 5 at a time, which there's only one way to fail every time. So that would be a 1 times the probability of success is 1/2, but we have done that 0 times, and the probability of failure is 1/2, and we have failed 5 times. So when you look at that, that ends up being 1 out of 32. Let me alternate colors here. Okay, then the combination for this would be 5, 1. Combination of 5 things taken 1 at a time. So we have succeeded with the probability of 1/2 once, and we have failed also with a probability of 1/2 4 times. Well, there are 5 ways to organize a group of 5 things taken 1 at a time. So we end up with 5 30 seconds. All right, then let's keep going. We'll go back to black. So now we're choosing 2 at a time. So we'll have 2 successes. And so it will be 1/2 squared and 1/2 cubed. Now you'll notice, this is an important thing, we're dealing in this case with a probability where we're equally likely to succeed and fail. So the back part of that, the right-hand part, will always be 1/2 to the 5th. So we'll continue with that as we keep going down the table. We don't have to keep separating the probability of success and failures because there's repetition. Now this ends up being 10 30 seconds because there are 10 ways to organize, to group, I should say, 5 things selected 2 at a time. And we can keep on going here. The combination, this will be 5 chosen 3 at a time, and we'll just put 1/2 to the 5th. All right, and this is also 10 30 seconds. It doesn't, it's a chance of getting 3 that would be 3 heads is the same as the chance of getting 2 heads because we're just switching up what the heads and tails will be. So continuing on, this will be 5 4, so that times 1/2 to the 5th, All right, and there are only 5 ways to select 4 objects at a time from a group of 5. Looking at combinations, not permutations. And then this will be 5, 5. There's only one way to take all 5. Okay, so we end up with 1/32 again. Now here's a very important thing. We should be able to add these up. If we total up our probabilities, notice I kept the denominator of 1/32, even when you get up to here in a case like this, obviously you could reduce that. It's not helpful because we're going to want to see, we want to compare those probabilities directly. So it's best to keep them all out of 32. And when we do that, we can see that we ended up with 1 plus 5 plus 10 plus 10 plus 5 plus 1 all over 32, which is 32 over 32. And that's a good thing, because if we said, what is the probability of getting 0, 1, 2, 3, 4, or 5 heads when we flip a coin 5 times, it has to be 100%. We could also, we're not going to do this right now, but we could take this distribution to quickly, now that we have it, say what is the probability of getting 4 or more heads, and we could just add the last 2 groupings here, and we could quickly see how to get 4 or more. It would be 6 out of 32 would be the chance of getting 4 or more heads. So once you have the distribution, it's easy to do, tell a lot about it. Okay. Now, one of the things that we should be able to do in this section is figure out how to graph this distribution. And this lends itself to what is called a histogram, right? Although it's a little different than a histogram because we're not counting the frequency of things. We haven't run the experiment actually. So we're talking about the probability of getting things. So on the vertical axis, we'll simply have a probability. We'll put a P. All right. Now let's put some markers on here. Since we have 30 seconds, let's make, oh, this is going to be a little tricky. Let's make this, how do we want to divide this up? We'll make that 4, 8, 12, and that's as high as we need to go. Actually, maybe we should spread that out a little bit more since we can, to graph this. Let's make each division be something like a 2. All right, the biggest we go, the highest we go is up to 10/32. So if I make a graph that looks like this, here's 0, 2, there's 4 30-seconds, 6, 8 30-seconds, 10, and 12 30-seconds. All right, so these are the probabilities on the y-axis, that P over. All right, and then on the x-axis, we have the number of occurrences. All right, so this would be 0 heads. We could put 1 head right here, 2, 3 heads, 4 heads, and 5 heads. And I guess I should probably shorten up my line a little bit, but I'll leave it for now. Now we want to put in our boxes of the histogram. So we could see that the chance of getting 0 heads was 1 in 32. So that's halfway here. And we'll make our boxes sort of a half unit wide, and we'll evenly space them to both sides of the number of heads that we're counting. Then the next one was 5, so that went up to here, 5 30-seconds. So we get a histogram that looks sort of like that. For 2, it went all the way up to 10, so that's right up here. So half a unit to either side of that. And then it was 10 again. And then it dropped down to 5, and then we were back down to 1. So you have a histogram that looks something like this. So the most likely outcomes are clearly to get 2 heads or to get 3 heads. They're just as likely, because if I get 2 heads, I get 3 tails. And if I get 3 heads, I get 2 tails. So there's no reason to prefer one over the other. So it's most likely that we would fall somewhere in the middle at 2 heads or 3 heads. Now, what I want to do is actually switch over to a computer simulation to show you that what is most likely to happen is not necessarily what does happen. when we run an experiment. So let me switch screens. So I've switched this over to a MATLAB simulation, all right? And in the simulation, we have 5 trials. We're going to toss a coin. What makes this a coin? It doesn't necessarily have to be a coin, but it has to be something where there's a 50% chance of success on each of those 5 trials. And then what we have down here, we're going to do a Monte Carlo simulation, right? We are going to flip a coin 5 times in a row and then repeat that 10 times. So for each set of 5, we will count how many heads we get, and we will do that 10 times over. When we run this, we can see a histogram. In red, we see something that matches what we just plotted on the iPad. All right, so we can see that's the ideal. That's what's supposed to happen, right? But when we did actually run this and we have a random generator for giving us heads or tails, we end up with a distribution that doesn't quite look like what we have here. We do have more flips towards the middle. 2 and 3 happened the most, but 1 happened more than it should have, and 4 and 5 and 0 didn't happen as much as they should have, or they didn't come up as often as we would have expected. So that happens if we run it once. Let's run it a couple of times. This time, we can see we had a very different result. Very different result again. Very different result again. So the point of this is that when we have low numbers of trials or simulations, so we're flipping 5 coins or flipping a coin 5 times in a row, maybe it's good to think of this as flipping 5 coins all at once and counting up the number of heads. When we repeat that 10 times, it's very unpredictable what could happen. This is what makes things like games fun. You don't know what's going to happen if you do something just a few times. But as we do it more and more, so let's say we take our 5 coins and toss them, but instead of doing it 10 times, we do it 20 times, we'll see a greater degree of predictability here. So if we run this 20 times, it's clustered a little bit more towards what we would expect. It's still pretty erratic though. So let's go up significantly more. Let's go up to 50 times. If we were to run the experiment of tossing 5 coins or flipping 5 coins and running it 50 times, we can see the outcomes are closer to what we would expect. Let me actually get rid of the clear figure so it doesn't disappear in between clicks. So the outcomes are definitely getting closer, but still that one's not that close to what we would expect, but we're definitely getting some zeros, some 5s, and we're getting more 2s and 3s than other things, but not always. If we run this a couple of times, occasionally, looks like 1 came up almost as much as 3. In that case, 1 and 2 came up the same amount, and 3 came up a lot more. But if we make this much larger, let's go right to 500. Right? If we run the experiment 500 times, we can see it's becoming very close to what we expect. It differs a little bit, but not much. And if we run it 5,000 times instead, we can see it's extremely close to what the predicted outcomes would be. So when you calculate your probability distribution, you're just predicting what should happen. It's not necessarily what will happen. But if you do run the experiment many, many, many times, it's likely to average out to what your distribution predicts. All right, so now let's change this up. Let's see if it's more predictable if instead of having 5 coins, if we have 50 coins. And let's start by flipping 50 coins in the air. The nice thing is the computer will count the heads and tails very quickly for us. And let's run the simulation 100 times over. Actually, let's start with just running it 10 times, see what happens. Okay. So you can see with 50 coins being flipped, we can't see how many times the 10 experiments fell on each event, but we can see that they tended to cluster more towards the middle. We were able to get, with 50 coins being flipped, we had at least It's like 18 heads was the minimum. And usually we were getting 23, 24. We were somewhere very close to 25 heads out of the total. Now, if I make that 100 flips, or 100, it's still 50 flips of coins, but we're trying it 100 times over, we see that's starting to get closer to the distribution that we calculated. But there's still a fair amount of erraticness in the experiment. That time we didn't get 25 very often at all. But there's definitely a cluster towards the middle. We're not seeing numbers below 15. We're not seeing many numbers above 35. So we're it's very likely that we will in fact cluster towards the middle, like our distribution predicted. If we were to change that to 100 simulations of the 50 coin toss, we can see it's very, very close to what we predicted. You can see some small differences, but it's basically becoming very much like the curve that we have here. And by the way, you may recognize this curve. It's starting to look more and more like the shape of a bell. In fact, this is approaching a bell curve. Let me double the number of tosses. And we can see it's a smoother curve like a bell curve. And if we simulate this enough times, the outcomes end up being extremely close to this bell curve that we have.